Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello, lesson 3. Hello, scaling principle for area. The scaling principle. Classwork Exploratory Challenge. Complete part 1 through 3 of the table. 1, 2, 3. For each of the figures in questions A through D, here's A, B, C, and D are on page 2. Determine the scale dimensions of the figure based on the provided scale factor. And 3, determine the area of the dilated figure. Then answer the question as follows. In the final column of the table, find the value of the ratio of the area of the similar figure to the area of the original. Okay. So it's an exploratory challenge, classwork exercise. Pause the video, see if you can do this. And here we go. Okay, so here's A. Scale factor of 3. Area of the original figure. Well, we have to find the area of this. So I would say A equals B. No, it doesn't. Well, I can do it this way. Base times height divided by 2. That's the same as 1/2 base times height, which equals 8 times 3 divided by 2. And that would reduce to 4, and the area is 12. So the area of the original figure is 12. Scale factor of 3, dimensions of the similar figure. Well, to find the dimensions of the similar figure, we take 3. Let's do it this way. Let me just show you this way. We have base times height, and we're going to multiply that by 3, scale factor of 3. Distribute, and that will give us 3b times 3h. So if we triple it, and b is 3, or the base is 8, I'm sorry, b is 8 times height 3, and I distribute it, I get 3 times 8 is 24, and 3 times 3 is 9. So the dimensions of the similar figure are 24 by 9. So I'll put that right here. 24 by 9. The area of the similar figure is therefore 24 times 9, which is 240 minus 24, 220, 216. The area of the similar figure is 216 units squared. Did I do that right? 9 times 4 is 36. Carry the 3. 9 times 3 is 27. 27 plus 3 is 30. No, hang on. What am I doing? Okay, that didn't make sense to me, and now I realize why. So let me just fix this. 216 is not correct. I didn't divide by 2. It's a triangle. 1/2 base times height. I have BH over 2 here. I did not put this over 2. So this was all correct. I get 24 times 9 over 2. And that is 24 times 9 is 216 like I had. But I didn't divide it by 2. So the area is 108 units squared. Okay. All right. So the ratio of the areas, area similar to area original. Here's the area of the similar figure, which is 108. And you can draw it as a fraction instead of the colon. And the area of the original figure was 12. And that reduces to 9. Okay, so the scale factor was 3. The ratio of the scale factor's areas was 9. 108 to 12, which is a scale factor of 9. All right. All right, so here we go. Part B. B is this triangle right here. So area equals, I'll put the half in front this time so I don't forget it, 1/2 base times height. So the area of this triangle is 1/2, the base is 5, and the height is 3. Okay, when we have an obtuse triangle, this is how we do it. The base is 5, the height is this right here, which would be over here as well. Okay, and so the area is 1/2 times 15. So the area is 7 1/2 or 15 halves. So I'll go back here and the area of the figure is 7.5. Let's do it as a decimal. And then they want us to scale it by 2. So I go back. And so if I scale that by 2, then the area, scaled by 2, I'll put a sub 2 down here, equals 1/2 the base. So it's going to be 2 times the base, 2 times the height. Okay, so we have to double both. So the area scaled up 2 will be 1/2, 2 times 5, and 2 times 3. So the area scaled up by 2 will be, and this 1/2 will cancel the 2, 5 times 3 times 2 is 6. The area squared is 30. And it is a 10 by 6, doubling this. Okay, 10 by 6. So this is 10 by 6, and the area was 30 because 10 times 6 is 60, half is 30. So the ratio of the area is 30 to 7.5. And 7.5 and 7.5 is 15, and there's 2 15s in 30, so there are 4 7.5s in 30. Okay, part C. All right, this is a rhombus or a parallelogram. I don't know for sure it's a rhombus because we don't know that those 4 sides are all equal. So it's a parallelogram. So the area equals base times height. So the area equals base 4 times height 5, or yeah, base 5 times height 4. So the area equals 20. So the area of the figure is 20. And we're going to scale this down by 1/2. So the area, half of it would equal 1/2 the base times 1/2 the height. So area 1/2 scaled down would be 1/2 5 times 1/2 times 4. So area scaled down 1/2 will be 5 halves times 2, half of 4. Well, think of that as 2 over 1, the 2's cancel. Area scaled down 1/2 comes out to be 5. So the sides were 2.5 and 2, right? 5 halves times 2. So, whoops, wrong way. So this was a 2.5 times 2 area. If I scaled it down 1/2, it was 5 by 4, half of 5, half of 4. And the area of the similar figure is 5 halves times 2, which is 5. Keep going the wrong way there. 5 units squared. So the scale factor ratio was 20, and now it's 5. And so therefore, oh, wrong way. I did it upside down. It says area of similar 5 to the area of the original, which equals 1/4. Okay, and then finally D, D is down here. Let's do that in purple. And area equals base times height of a parallelogram. So substituting in my givens, the base is 3, the height is 2. So therefore the original area is 6. So I go back, I put that here. Area of original figure 6. And this time we're scaling by 3 halves. So to scale this by 3 halves, I would say the area of a scale of 3 halves would equal 3 halves times the base times 3 halves times the height. So the area scaled 3 halves will become 3 times 3 is 9 halves times 3 times 2, which is, well, the 2's cancel and I just get 3. So think of that as 3 over 1. And so those are my sides. 9 halves is 4.5, 4.5, and 3. So it's 4.5 by 3. Okay, and then we multiply that and we get the area of a shape scaled up 3 halves is 9 times 3 is 27 divided by 2, which is 13.5. So I put that in my table. Area of similar figure is 13.5 units squared. And I suppose I should have units squared over here as well, but that's okay. Area of similar, 13.5 divided by 6. Okay, let's just use the calculator for this to save time. 13.5, forgot the decimal, 0.5 divided by 6 is 2.25. Okay, 2.25, 2 1/4, 5 quarters. Right, if I hit math, enter, enter. Oh, sorry, 9 quarters. All right, that's why I was questioning. It didn't look right. 9 quarters. And why am I saying it didn't look right? Because what this lesson is showing us is, look what happens. If we have an area of 12 and we scale the sides by a factor of 3, then the area factor changes by 9, which is 3 squared. If we take 7.5, an area of 7.5, and we double the lengths of the base and the height, then we get 30, which comes out to be 4, which is 2 squared. If we take 20 and scale it down by a half, okay, and we end up with a ratio of 1:4. So that would be 1/2 squared. 1 squared over 2 squared is 1/4. And then finally take 6, multiply each side by 3 halves, the base and the height by 3 halves, gave us these values. And we ended up with a scale factor of the area of 9:4, which is this squared. Okay, so if you have an area and you scale the lengths of the sides of the object by a ratio, then its area is going to be squared that ratio. All righty. Okay, part E says make a conjecture about the relationship between the areas of the original figure and the similar figure with respect to the scale factor between figures. So here it is. Hey, that's not it. Momento. There it is. It seems as though the value of the ratio of the area of the similar figure to the area of the original figure is the square of the scale factor or of dilation. Okay, and that's what it is. Okay, so it says here the scaling principle for triangles. What is the scaling principle? Okay, here it is. Let's make that a little larger. Oops. struggling here today. There we go. If similar triangles S and T are related by a scale factor of R, then the respective areas are related by a factor of that R squared. The scaling principle for polygons. If similar polygons P and Q are related by a scale factor of R, then their respective areas related by a factor of R squared. So it's the same for triangles and polygons, because a triangle is a polygon. Poly meaning many, sides, polygon, many-sided figure. Triangle has 3 sides, so it's a polygon. Exercise 1.12. 1-2, 1 and 2, and a 1 and a 2, and here is a 1. Rectangles A and B are similar and are drawn to scale. So we're told they are similar. They have 4 90-degree angles, and their base to their height ratios must also be the same. So if the area of rectangle A is 88 millimeters squared, what's the area of rectangle B? So here's where writing the formula every time comes in handy. So here we go. Write the formula. A, area, equals base times height. Substitute in the givens. The area of the rectangle A is 88 millimeters squared. So over here, I'd put 88 millimeters squared equals the base, which is 16 millimeters, times the height. So if you write the formula, substitute in the givens, then you just solve for the variable and you're done. So divide both sides by 16 millimeters. The 16 millimeters cancels here. The 16 millimeters cancels here. The millimeters cancels this millimeters squared, making it just a millimeter. And 88 divided by 16 is 5.5. So the height of this rectangle is 5.5. So H equals 5.5 millimeters. Okay. Okay, so now the ratio of the two sides is 16 to 30. So our R, let me change colors for this, our ratio is 16 to 30 from A to B, A over B. And that reduces to 8 over 15. Okay, so that is our R right there, 8/15. So if I take 16 times 8/15, I should get 30. 16 times 8 divided by 15. Wait, what? Okay, I went the wrong way. Hello, my fault. All right, so whenever something doesn't make sense, question it, because that did not make sense to me. So I questioned it, and then I got thinking, oh, hello. We're going small to big. That's a factor of greater than 1. So the bigger number has to be on top, and it's 30 divided by 16. What did I do? 30 divided by 16 equals 1.875. And that reduces to 15/8. I think I had 8/15. So then if I take 15 over 8 times 16, 16 times 15 over 8, then I should get 30. There we go. That's better. Okay, so then why am I doing this? Well, I need to know to find the area of this. I don't know the area and I don't know the height. So I had to find the height using the scale factor. So now that I know the scale factor is 15/8, I can take the height of A and multiply it by that 15/8. So 15 over 8 times the height will equal the height of B. So I should have a little a there. So 15/8 times the height of A equals the height of B. So 15 over 8 times 5.5. Let's make that a fraction. 5 1/2 is 11 halves, and that's going to equal 165 over 16. Okay, and I'll check that. 15 divided by 8 times 11 divided by 2 will give me 10.3, which is 165 over 16. So did it come out to be exactly 10.3? 10.3125. So that is this, 10.3125. So now the area of this one is area of B equals base times height. The area of B is going to equal the base, which was 30, times the height, which is 10.3125. So I take this and I hit times 30, and I get 2,475 over 8. So I hit math, arrow down to 2 for a decimal, and hit enter, and I get 309.375. So the area of B equals 309.375. So let's check our thing up here. If our scale factor was 15/8, then R squared equals 225 over 64. So that is our ratio of areas. And I found the area is 88 millimeters. So if I take 225 divided by 64, and I multiply that by 88, I should get this same number. And there it is. Okay. So I didn't have to go that far, and I did not have to find the height. I'm just showing you in this process. We found the height here because we knew the area. What we really needed to do is just simply find the ratio of 30 over 16 and then square that. Take that value, multiply by your area, and you get the same answer. Okay. Okay, page 4 brings us to problem 2. Now we need to be really careful when we're doing problems, because sometimes they try to sneak one in on us. Trick us. Figure E and F right here. They're rotated, they're flipped. Okay. They're similar and are drawn to scale. So they're rotated, flipped, and dilated. And E is big and F is not so big. So we're going from larger to smaller. So our scale factor is less than 1, but greater than 0. But notice this CM here and this MM here. We can't do a problem until we are in the same unit of measurement. And 2.4 centimeters is 24 millimeters. So be careful with that first step. Okay, this will be all wrong if we forget to convert centimeters to millimeters, or vice versa. Okay, but I look at the answer up here, and the area of figure E here is 120 millimeters squared. So we want them in millimeters, not centimeters. So the area of this is that. What is the area of this figure? Well, the first thing I want to do is find R. And R equals the scale factor from F, the image, to the pre-image. And how do I know which is which? We are scaling down. We want our R to be less than 1. If the numerator is greater than the denominator, then it's a scale up, larger. We want the smaller number on top. So R is F over E, which is 15 millimeters over 24 millimeters. And 3 will go into 15 5 times. And 3 will go into 25 4 8 times. So our ratio is 5/8. So if I square that, then my scale factor of my areas will be 25 over 64. Okay, so all I need to do is take the area of E and multiply it by my scale factor squared. So I'm going to take 120 times 25 over 64. And when I put that in the calculator, 120 parentheses 25 divided by 64, I will get 46, approximately, I'm going to round, 46 point, and does it say what to round to? No. 46.154. Let's go out 3 decimal places. The 8 will make the 3 a 4. 154 millimeters squared. So that is the area of F. 120 times the scale factor squared. Okay, so we didn't need to know, all we need to know is corresponding sides, one side to one side. Okay, so I noticed something here. This is not right, because I know I punched something in wrong in my calculator. This should be 0.875. I noticed I punched in 25 over 65 in my calculator. I was off by 1/65th, so that was off by a little. So the answer should be 46.875 millimeters squared. Okay, the scaling principle for area is if similar figures A and B are related by a scale factor of R, then their respective areas are related by a scale factor of R. So this is a scaling principle for all areas, is basically what we're leading up to. So we started with triangles, then we did polygons. Well, this is still a polygon, so would it work for a circle? Okay, page 5 brings us to the end of lesson 3. Review the lesson summary and go to your problem set.